growth models and the differential equations. So recall from a previous lesson that the exponential growth can be modeled by the differential equation dy dx equals k times an x, and it has a general solution of this right here, some constant times e to the kt. So, but when we are discussing population growth, we have a problem, and it's this: the model is not realistic. Populations don't grow forever without some kind of limiting factor. So we need some kind of new model to mimic this one, and that's the logistics growth. So here's the logistics growth model. Okay, it will look just like an exponential up to a certain point, and then it will start flattening out because of disease, for populations, disease, wars, things like that, starvations and things like that, just general death rates limit the amount that can happen here. This model gives a better representation of population growth over a longer period of time. For a short period of time, we can use an exponential growth, but for a long period of time, we want to use this model because it's more realistic. The logistics growth is modeled by the differential equation, and here is two forms of these. You want to make sure you recognize both of them. Okay? It will help you tremendously. So you want to be able to recognize both formats that's here, and the general solution looks like this. It's hard to read right here. This is e to the negative a times k times t. When y is less than or equal to a over 2, the graph resembles the graph of an exponential growth and such. So when we are less than halfway here, then it looks just like this one up here. It acts the same exact way. Okay? And so with that in mind, we're now going to look at some characteristics that will be asked of you on the AP exam. Things you need to know about the logistics growth. As y approaches a, dy dt will approach 0. Well, what is a? A is this top number up here. As y gets closer to a, then it turns more and more horizontal is what it's telling you. Okay? The limit of the function as t goes to infinity is a. Y equals a is called the carrying or limiting capacity. This is the maximum amount that can occur. That's an important number. You'll see that quite a bit in your problems. Dy dt equals 0 at y equals 0 and at y equals a. Okay? Y of t is always increasing, so dy dt is always positive. Y of t is concave up on the first half and then concave down on the second half. So this is where a point of inflection occurs. Concave up here, concave down here. So that is a point of inflection. And it's also the y of t has a point of inflection at y equals a over 2. This is when dy dt is at its maximum value, which is y of t is increasing at its greatest rate. Remember that phrase? It's going to be used in your problems. When is this function, or when is this population increasing at its greatest rate? That is going to be the a over 2 number. Okay? So let's look at some of the question types that you're going to be seeing and how they'll ask it and get familiar with it. So we have our first example. P of t denotes the population of a city in thousands of people at the time t, and its growth is described by the differential equation, this right here. So you can see it's in the format of the logistics growth model. At time equals 0, the population is 10,000. What is the limiting population of this city? Okay, so they want to know, so for our answer, they want to know when is dp dt equal to 0. Well, we already know the two places that's going to occur is when p equals 0 and p equals 30. So why? So what is the limiting population? Is 30 1,000 because people are in thousands. All right, part B. So when is the population growing the fastest? So that is that midpoint value. It is growing the fastest when P is A over 2. A is the 30,000. So this is going to be when 30,000 divided by 2, or 15,000 people. When is the population graph concave up? When the population is less than the 15,000. When is the population increasing? dp dt is greater than 0 for all t values, for all time values. So the population is always increasing. Okay? All right, so there we go. So let's backtrack to this right here. I think I glossed over this just a little bit too fast. So let's look at the model, the dYdt model here. So here we have dP dt. In a logistics growth format, this is some number times P times A minus P. So if this is our format right here, I have this. Excuse me. I have this. Okay? So what are these values in here? All right? So if I look at this right here, I need to get rid of that 2. Okay? So if I divide everything by 2, this divides by 2, factor out this, 1/2, then what is half of 60? That's where I got that from, by the way. Because I need to have a number 1 in front of this P right here. So divide by 2, bring it out here. That turns into a 30. That's where that 30 came from. Sorry, I didn't express that before. And so that means it's in thousands, so it's 30,000 people. So that's where it came from, was matching this formula right here. Okay, let's look at another example that could be asked of you. The rate of change of the number of lines on an island, L of t, is modeled by a logistics differential equation. If the rate of change of the population is at a maximum when there are 300 lions on the island, and the rate of change is 20 lions per day when there are 500 lions on the island, write a differential equation to model this situation. So you need to know your model form. And lions, L of t is the variable, function variable. So it's dl dt for lions. Some number times the lion population, A minus L. See, so we want to fit into that format. So we look around and see what they told us. Okay? The population is at a maximum when there are 300 lions on the island. That maximum is that mid number. And so that means when the lion population is that A over 2, it should be 300. So that means A has to be 600 lions. That is our carrying capacity. That's the most number of lions you can have on this island. Okay? So once I have that number, then I know from right here that the rate of change is 20 lions per day when there are 500 lions. Okay? That means dl dt is 20. I don't know K. That is when there's 500 lions on the island. This is 600 minus 500. So if I work all this out, okay, this will be 100 and divide everything out, I get K is equal to 1 over 2,500. And once I have that, then I can plug everything into my differential equation right here and get 1 over 2,500 L, 600 minus L. And that is my differential equation. So we want to learn the characteristics of the logistics growth function to help us in answering the questions that are going to be coming at us. I got a couple more examples here. Let's go ahead and take a look at the next one. So the number of mice on a large farm is modeled by this function right here, m, where t is measured in weeks. M of t is the solution to a logistics differential equation of this form right here. At t equals 0, there are 20 mice on the farm. As time increases without bounds, that just means it goes on forever, how many more mice will be on the farm when it reaches its limiting capacity? So a lot of stuff going on here. And first thing is we want to put this into a format that we are familiar with. Okay? So however you want to look at that, I recommend that you get it to look into the format of dm dt is sum k times m a minus n. I would try and get it into that format right there, which means I'm going to have to divide by stuff. Okay? I want to get rid of, now, so I'm going to divide by 3m over 125. So I'm going to bring all that out, and so this is going to look like 3 over 125 times m, and then what's left? Okay, so if you take this thing right here and divide it by, flip everything over and divide by that right there, you're going to get 250. So you're taking the 6m and dividing it by 3m over 125. So if you do that, you're going to get this number right here, and then you're left with just the m over here. And that's now makes it easier for us to look at this question. So the carrying capacity, so A is going to equal 250. Okay? And so the question was, at t equals 0, there are 20 mice on the farm. As time increases without bound, how many more mice will be on the farm when it reaches its limiting capacity? So I have 20. This is the capacity. So literally I want 250 minus 20, or 230 more mice. Okay? And so here's the last one for this video. The number of fish in a lake is modeled by the function f of t that satisfies the logistics differential equation, this one right here, where t is the time in months and f of 0 is 2,000. What is the limit as t goes to infinity of f of t? So this is just literally another way of asking you, what is the carrying capacity? Okay? What is the carrying capacity? So you can do a couple things. You can either, if you remember back in the beginning of this thing, I said you want to remember the two different formats. This is one format, this is what we've been using, but the other format looks like that. And if we compare it to what we have over here, we have, here's the generic format we're going to use, some number times a y, and then 1 minus y over a. If you look at that, y being the function that we're talking about, you will see that f plays the role of y, and so a is 5,000. So we can see it right there without having to do anything else. You obviously could factor out 1 over 5,000, okay? And when you do that, this number right here in that format will become 5,000, so you can see that a is again 5,000. So what is the limit as t goes to infinity of this function? Well, it's simply just going to be 5,000. The carrying capacity. Okay, so complicated looking questions, actually very simple if you know the characteristics of a logistics growth function, okay, and what everything means, the carrying capacity, when is it growing the fastest, and that things like that. Okay, so that ends this video, and if you have any questions, again, make sure you let me know.